All right, here we go. Today we are looking at solving equations, specifically section 3.5. Since we're in our chapter on exponential and logarithmic functions, we're going to be solving those types of equations today. We're going to start with exponential functions and then move into logarithms. So let's start with our first exponential equation. I think you're going to find that these are pretty easy. All right, our first example, 24 times 1/2 raised to the x over 3 power equals 96. With an exponential equation, you want to start by isolating the base and the exponent, which means in this case, on the left side, I only want to see this base of 1/2 and the exponent x over 3. Anything outside of that, like the 24, I want to get rid of that first. So we're going to, in this case, since 24 is being multiplied by that value, we'll divide both sides by 24 so that we can isolate that base. In which case, we will end up with 1/2 to the x over 3 equals 4. When solving exponential equations, there are two ways that this process can continue from this point, once you have the base isolated. You can either rewrite both sides of the equation in terms of the same base, or you can change it into logarithmic form and solve it that way. And we're going to do an example of each. In this case, I know that 1/2 is a power of 2, specifically 2 to the negative first power. I also know that 4 is a power of 2, 2 squared. So if we rewrite both sides in terms of that base of 2, this side becomes 2 to the negative x over 3 power, and the 4 becomes a 2 squared. So what I see at this point is I have two quantities that are equal to one another. They happen to have the same base, which means their exponents must be equal. So negative x over 3 must equal 2. The exponent on the left equals the exponent on the right. If I solve that for x, I'm going to multiply both sides by negative 3. Yeah, x equals negative 6. Now, it is in your best interest to check those and make sure it works. When you do your check, substitute that value of x into the original equation. Don't use one of the intermediate steps. Go back to the original. So in this case, 24 times 1/2 to the negative 6 over 3. Now, if this checks correctly, that quantity should equal 96. So, let's see, simplify the exponent. It's negative 6 over 3 becomes negative 2. We know that 1/2 to the negative first is 2. When I square that value, it becomes a 4. So this is 24 times 4, which is indeed 96. So since that checks out, we know that this value is correct. If it doesn't check, you want to make sure that you've done the intermediate work here correctly. If those steps are still correct and it doesn't check, then you may have an equation with no solution. All right, so let's look at another example then, number 2. 5 times 3 to the x power equals 25. Same steps as before. I want to isolate the base and exponent, so I'm going to divide both sides by 5. So 3 to the x equals 5. Now, in this case, I can see that there is no common base that I can use. That would be 3 and 5 are not both exponential powers of some base, like they were over here with the 2. When that happens, you want to change it into logarithmic form. And remember, in your log form, you have your base here, the value in this case, whatever that number happens to be, and then our exponent is over here on the right. So in this case, the log with a base of 3 of 5 equals the exponent x. Now this particular one, there is no power of 3 that equals 5, at least not a whole number. there is a value, just not a whole number. So it's in this situation that I would go to my calculator. And if you're going to type that into your calculator, you're going to do it one of two ways. If your calculator happens to have the operating system where you can change the base and make it any value, then you're going to type it in just as it looks here. If it doesn't, then you're going to use the change of base formula and do log of 5 over log 3. Remember, your base goes in the denominator. You can also do this with a natural log 5 and a natural log 3. You can do it with any base. But if you're using that change of base formula so that you can type the value into your calculator, then I wouldn't suggest changing it to like log base 2 of 5 and log base 2 of 3. That wouldn't get you anywhere. Here I'm using a common log. I could have also used a natural log, and it's going to give me the same result. And I'm using those functions because that's what's available on my calculator. So log 5 divided by log of 3 gives me an answer of approximately 1.465. It depends on the context of the problem that you're in, what the directions have told you, etc., as to whether or not you want this estimated version, where it's been rounded, or if you want the exact value, where no rounding has taken place. Either one would be correct. They give you the same answer. It's just a matter of the context as to which of those you're going to provide. And like I said, that's typically going to be specified in your directions or in the context of the problem that you're working with. All right, so now let's look at a logarithmic situation. As with their exponential counterparts, in a logarithmic equation, you want to start by isolating the logarithm part. So if there's a coefficient out to the front, we want to get rid of that first. So our number 3 here, we are going to do 2 times the log of x equals 6. Okay, there's a couple of ways that we can do this. I could, using the power rule for logarithms, I could take this 2 and move it back into the exponential position, or the exponent position rather. I'm not going to do that in this case, but you could. All right, instead I'm going to get rid of this 2 by dividing it on both sides. Because that is a product, you can divide by that coefficient, and that's going to leave us with the log of x equals 3. Now at this point, when you've got a logarithmic equation where your variable is contained in the logarithm portion, if the variable's over here, then you're in a situation where you just type it into your calculator. But whenever you have your variable as part of the argument in the logarithm, then you want to change it into exponential form. In this case, our base with the common log is understood to be a 10. And remember, this one over here is your exponent. So in this case, the exponential form would be the base of 10 raised to the exponent of 3 equals x. And hopefully we all know that that means x is 1,000. And that is that. Now, in terms of checking that, if I were to check it, 2 times the log of 1,000. Think about what we did with logarithms. 10 to what power equals 1,000? That's what the logarithm means. So 10 to what power equals 1,000 would be 3. And 2 times 3 is 6, which is what it should have been based on the original equation, which means our value of 1,000 is correct. And that's one way to do a logarithmic equation. Another thing to be aware of with logarithmic equations is that sometimes you'll be given an equation where condensing the logarithms is going to be useful before you solve the equation. What we want this side to have is a single logarithm, if at all possible. So in this case, let's look at the equation log base 5 of x minus log base 5 of 7 equals 4. Okay, so what we know about condensing logarithms, when it's a difference of two quantities, then condensing it makes these become a quotient. So in this case, we have the log base 5 of x over 7. And remember the first one here, the positive term, that's the one that goes in your numerator. The one that's with the negative or the minus is going to go in your denominator, equals 4. So now we have a single logarithm to work with, and we're going to treat it much the same way that we did the last problem. In this case, we're going to change it into exponential form. So our base in this case is 5, exponent is 4, equals x over 7, that quantity. Alright, so 5 to the 4th would be 5 times 5 is 25, times 25 is 625, equals x over 7. Multiply both sides by 7 to get x by itself. And we end up with 4,375 for x. And that would be our solution then to number 4. And we're going to do one other logarithmic equation, and this one's another one that involves condensing in order to solve the equation. But I want to introduce it because it is slightly different than this simple quotient that we had in this case. So let's look at number 5. The log base 6 of x plus the log base 6 of the quantity x minus 5 equals 2. Alright, so we condense it in much the similar way that we did last time. We know that in this case we have a sum, which means when we condense, these will become a product. So in this case, the log base 6 of the quantity x squared minus 5x. And I've gone ahead and multiplied those together. You'll see why in a moment. And that, of course, equals 2 on the right side. Alright, so change to exponential form. 6 to the second power equals x squared minus 5x. Now you should recognize at this point that what we have is a quadratic equation. So if we go ahead and square that 6, with quadratics you want to set them equal to 0 and then factor or use the quadratic formula. So in this case, set it equal to 0 by subtracting 36 on both sides. And this one does factor, so we'll go ahead and do that in the next step. Factors into the quantity x minus 9 times the quantity x plus 4. At this point, we should be able to see that there are two possible solutions, x equals 9 or x equals negative 4. And here's where our check comes in, and the check is crucial on a problem of this type. So for my check, on this first term I have the log base 6 of 9 plus log base 6 of 9 minus 5, or 4. Go ahead and combine those. It's going to become the log base 6 of 36. In other words, 6 to what power is 36? And that's where we get a 2, which is what it should have been. So this x equals 9 is correct. We've checked that one. Now let's check the other one. So log base 6 of negative 4 plus log base 6 of negative 9. And here's where we have a problem. As you may or may not recall, in a logarithmic function, it has a vertical asymptote on the y-axis, and its general shape increases as it goes to the right. You'll note that no input value that's negative can be used in the domain of this function. The domain of that function has to be from 0, which is not included because of the asymptote, up to infinity. Which means in this case, the variable x cannot be a negative, which takes this equation and makes it impossible, which means this solution is also impossible. So you have to check them, especially with these logarithms, to ensure that this value that's inside this quantity is not negative.